in the last lecture, we solved what is called the characteristic equation of a mode. We saw that in general, the characteristic equation is for the hybrid mode, whereas if we take nu equal to 0, that means if we take circularly symmetric fields, then we get the mode which are transverse electric or transverse magnetic. Then we defined a very important parameter for the optical fiber, what is called the V number of an optical fiber, which was given by 2 pi a upon lambda into numerical aperture, where a is the radius of the fiber and lambda is the wavelength of operation. So, this parameter is a more comprehensive parameter to characterize the optical fiber than the numerical aperture, and this parameter is proportional to frequency. So, we said this parameter is also called the normalized frequency. Then we found that there is a limit on the propagation constant, that is beta 2 and beta 1, or if we define what is called the effective modal index, then the modal index lies between the refractive index N2 and N1. So, we could define this quantity, what is called the normalized propagation constant, by this, where this parameter B lies between 0 and 1. And then we got the relation between the B and V, or beta and the V number, and we got this diagram, what is called the BV diagram of an optical fiber. And we found that the V number, which is a combination of the refractive index of core, refractive index of cladding and the size of core, together essentially decide the propagational characteristic. Individual parameters N1, N2 or A do not play a role in deciding the propagation characteristics. And then we found that as the V number increases, the propagation constant monotonically increases from beta 2 to beta 1, or the modal index increases from N2 to N1. Also, as the V number increases, then more and more starts propagating. So, all the modes have a cutoff, that means below certain V numbers, certain modes do not propagate, except this mode, which is HE11 mode, which propagates down to V equal to 0. And then we said this is the mode which must correspond to a ray which travels along the axis of the optical fiber. So, for single mode operation, essentially the V number must lie between 0 and this number here, which is 2.4. And then we mentioned the 2.4, this magic number, is due to the roots of the Bessel function. So, if I consider J0 Bessel function, then the first root of J0 Bessel function is 2.4. So, if we want the fiber to be single mode, then we must choose the parameters refractive index of core and cladding and the size of the core, such that the V number lies in the range 0 to 2.4. We also argued that if I look at this quantity beta, or if I look at the N effective, if N effective is very close to N2, that means there is more energy lying inside the cladding, whereas if N1 or N effective approaches N1, then the energy gets more and more confined to the core. So, ideally we should choose a V number which will make the N effective as close to N1 as possible, because that gives you more and more confinement to the core. So, if I look at this diagram here, ideally it means that I should use a very large V number, so that this curve here is very close to N1. However, if I choose a value of V which is lying somewhere here, of course, for HE11 mode, we have a very good confinement of the energy, but we also have a very large number of modes which are propagating. So, in fact, how do we find out the mode which are going to propagate? I just take a V number, draw a vertical line from that V number. All the modes which have a cutoff frequency less than this V number, those modes will propagate. So, for this line, this set of modes will propagate, this set of modes will propagate, HE11 will propagate. However, if I bring it here, only this set will propagate and HE11 will propagate. These modes will not propagate. So, by increasing the V number, yes, for HE11 mode, we can make a good confinement of the energy inside the core, but at the same time, other modes propagating inside the fiber, and these modes may not have N effective which is very close to N2. So, by choosing a high V number do not help us, because firstly it gives us large number of modes propagating, which gives more dispersion, and the energy which is going to be put inside the optical fiber get divided into different modes. So, part of the energy still remains inside the cladding. So, what that means is that if you want to have a single mode operation on the optical fiber, then since the V number has to be less than 2.4, I have to operate somewhere in this range, somewhere here. But V number has to be as large as possible. So, for single mode, this range from here to here is acceptable, but for a good confinement of the energy inside the core, the V number should be as large as possible. That is the reason typically the single mode optical fibers operate with a V number less than 2.4, but very close to 2.4, so somewhere here. So, if I take a V number, let us say somewhere here, something like this, you will see that N effective is almost halfway between N1 and N2. That means there is half the energy which is lying approximately outside the core and half the energy which is lying inside the core. So, we cannot have a single mode operation without having a substantial energy inside the cladding. So, a single mode operation gives you less dispersion because only one mode is going to propagate on this, but it has a substantial energy put inside the cladding. That should be understood. Now, just to get a quantitative number from this V equal to 2.4, just take some typical numbers for single mode operation. So, we want for single mode operation now V should be less than 2.4. We can write down V, which is 2 pi by lambda into A into numerical aperture, which is N1 square minus N2 square square root. This quantity should be less than 2.4. If I take, let us say, a typical number for the numerical aperture, which is about 0.1, then we can get 2 pi into A upon lambda, 0.1 should be equal to 2.4. So, from here we can get A by lambda approximately 2.4 divided by 0.6. This is 2 pi is approximately 6, this is 0.6. So, we get A by lambda typically of the order of about 4 for a numerical aperture, of course, for 0.1. If you make numerical aperture smaller, we can get A by lambda larger, but typically these are the values which you will see in practice. So, that means we get typically A by lambda about 4. So, if I consider typically a operating wavelength of 1 micrometer, we saw that there are windows 800 nanometer, 1300 nanometer or 1550 nanometer. That means in terms of microns, it is 0.8 micron, 1.3 micron or 1.55 micron. If I take just for a rough calculation, the lambda equal to 1 micron, then the radius of the fiber should be less than 4 micrometer. Then only the fiber will be single mode optical fiber. So, that is what we have seen while discussing the ray model, that if you make the core of the optical fiber very thin, then there is a possibility of single mode propagation on the optical fiber. And now we have got a quantitative answer that if you take typical parameters for the refractive indices for core and cladding, then if the core radius is less than about 4 micron or 4 to 6 micron, because the wavelength is going to range between 1 micron and 1.55 micron, then you will get single mode operation in the optical fiber. So, that is the reason the single mode optical fibers have a very small core, and as we mentioned earlier, that is the reason they require very special type of sources for launching light inside them, and these sources would be laser type of sources which have a very collimated beam. With this, now let us look at the field distribution which we are going to get for the modes. That having said that we have got the field expressions, at least first few modes we can have a look at, and if you look at the BB diagram, we have the initial mode, one is the HE11 mode, then you have a TE01 mode, then you have TM01 mode, and then you have a HE21 mode. All of them have more or less same cutoff frequency, which is corresponding to V number 2.4. So, if I take now the field expression, then the electric field for these modes would essentially look like that. So, if I take the HE11 mode, then that is the way the field would look like. That means, everywhere along the cross section, the field will be oriented in the vertical direction. As we move radially outwards, the field decreases, but the direction of the electric field remains constant. If we consider T01 mode, then as we have seen that the fields are circularly symmetric. That is what the fields are representing. So, fields have a component which is E phi. So, you have a field, electric field, which is going like this in circular loops. It has an intensity which is at the center. If I consider TM01 mode, then the electric field will be going like this. Again, you have a circular symmetry in this. And for HE21 mode, the fields would be like that. So, you can see here it has in azimuth, it has this index 2. If I go to this now, HE11 mode, the field is oriented everywhere which is like this. Let us understand how the two indices are giving you this field. So, as the name suggests, this is the hybrid mode, and the first index gives me a field variation in the phi direction, and the second index gives me the field variation in the radial direction, and if second index is 1, there is no zero crossing in the radial direction. So, that is very clear here. The second index is 1, the field is decreasing from the center to the edge, but no zero is crossed here. How do you see the first index? Which says you there is HE1, that means there is a 1 cycle variation here. If I look at the field component, which is like this, then consider any field component. Let us say I consider a R component, ER component. So, if I come here, the R is radially outwards everywhere. So, if I come to this direction here, the R component is 0. If I come in this direction, the R component is maximum. If I come here, the R component, which should be oriented this way, is 0. And when I come here, the R component is oriented in this direction, which is negative R direction, because R should be coming this way. So, you got 1 cycle variation here. It goes from 0 to positive maximum to 0 to negative maximum. Similarly, if I had consider a phi component, the phi will be in this direction, azimuth. So, if I take here, it is in the direction of phi. If I come here, the phi direction is this, but the field is oriented this way, that means the phi component is 0. If I come here, the phi direction is this, field is upwards, that means it is in the negative phi direction. So, you got a negative maximum, and when I come here, you get the phi direction this way, field is this way, so phi component is 0. So, what we find here is that both component, R component and phi component, they show you 1 cycle variation as we move in the azimuth. And that's what essentially this first index is telling you. So, HE11 mode, if I consider any of the components, either phi component or R component, will show one cycle variation in the azimuth, and there is no zero crossing of the field intensity when I go in the radial direction. So, that's why essentially the field is going to look like. Now, if I go in the practice, most of the practical fibers, as we have seen earlier, the difference in the refractive index between core and cladding has to be made as small as possible. That's what we discussed earlier when we were discussing the ray model. So, to get a substantial size for the core radius, because if I make the difference in refractive index large, the core size will become extremely small from here, because we want the V number for single mode propagation has to be less than 2.4. So, one possibility is I make the difference N1 and N2 very small. If I do that, then I can get A reasonably large. If I make this difference very large, then A will become very small. Now, since we do not want the A to go less than few microns for the light launching considerations, we want this difference between N1 and N2 should be made very small. So, in practice, therefore, what we have is this quantity, what is called delta, which is defined as N1 minus N2 upon N1. That quantity is much less than 1, because N1 is very close to N2. And imagine a situation, suppose N1 was exactly equal to N2. That means there is nothing like core or cladding now. You are having only one medium with refractive index. And if the light has to propagate in this medium like an electromagnetic wave, since there are no boundaries now, the light will propagate like a transverse electromagnetic wave. So, what that means is that when N1 becomes equal to N2, the longitudinal component of electric and magnetic fields vanish, because the wave becomes completely transverse electromagnetic. Obviously, this phenomena cannot take place suddenly when N1 is equal to N2. So, that means as N1 goes close to N2, slowly the longitudinal component becomes weaker and weaker, and the fields have stronger transverse components. So, for a practical fiber where N1 minus N2 divided by N1 is much smaller than 1, the Ez and Sz component would be very small, they will be negligibly small compared to the transverse components. So, we say that the fields are almost transverse now in this approximation. This approximation is also called the weakly guiding approximations. Why weakly guiding? Because if there was no boundary between core and cladding, if N1 was equal to N2, then energy will be uniformly distributed over the entire space. The confinement to the energy to the core is coming because it has a higher refractive index compared to the cladding. When the difference between these two becomes small, there is a substantial energy now which is lying inside the cladding. That means the guiding mechanism, because of the core, is becoming weaker and weaker. So, in the regime, when this condition is satisfied, we say the propagation is weakly guiding. And most of the optical fiber which are used have this weakly guiding approximation well justified. Because for these fibers, the difference in refractive indices for core and cladding is really very small. So, for a practical fiber, since the weakly guiding approximation is justified, the fields are almost transverse, and also one can show that the fields become what are called linearly polarized. What do I mean by that is that if I consider now a field which is like this, The field direction is continuously changing. So, I have a field direction like this here, like this here. So, if I consider a point here, the field will be oriented this way. If I consider a point here, the field will be oriented this way. If I have here, the field is going this way here, this way here, this way here, and so on. So, if I look at the cross sectional plane, the field direction is different at different locations in the cross sectional plane. What one can show is that if you have a weakly guiding approximation, then you have an intensity variation in the cross sectional plane, but as far as the direction of the field is concerned, it remains same practically everywhere in the cross sectional plane. So, it could be, if I is vertical, it will remain vertical everywhere. It may be positive or negative, but the field will not be oriented in this way. So, these fields then we call as the linearly polarized fields. So, two things essentially happen when we have a weakly guiding approximation, and that is the field become almost transverse and they become almost linearly polarized. In terms of BB diagram, what essentially is happening is that as the N1 becomes equal to N2 or approaches N2, then the mode which you see separately here in this group, they almost become degenerate. That means, this characteristic BB diagram for this set of mode, they almost merge into each other. Similarly, these modes will merge into each other, these will merge into each other. So, we will never see individual modes like T01, TM01 and HE21. You will always see a combination of these three modes which will be there, and this combination would generate a field distribution which would be linearly polarized. This mode, which is isolated mode, will be linearly polarized. That was already a linearly polarized mode. As you can see the field distribution, you have a polarization which is linear everywhere. But if I consider the second set, which is a combination here, even after these three modes become degenerate, that means they have the same phase constant, you will see the distribution which will be linearly polarized. So, in any practical fiber, we do not have the general hybrid or TE or TM modes visible, because combination of these modes which are degenerate always generate the field distributions which are linearly polarized. That is the reason normally the mode which propagate inside the optical fibers are designated by linearly polarized modes or LP modes. So, you will see in the literature, if you are treating the optical fiber as a simple waveguiding structure, then you would have the mode which will be hybrid modes or T or TM modes. But most of the practical situations, we will talk about the modes which are the linearly polarized modes. So, in general, then we can say that we can have now the combination of different modes which can generate the linearly polarized modes. So, if I take a HE11 mode, the HE11 mode will become the linearly polarized 0, 1 mode. Now, here the indices essentially are telling us, the first index tells me the azimuthal variation, and now note here, this is not telling you the variation of ER or phi component, it is telling you the variation of linearly polarized fields. So, if I say that my polarized field was vertically polarized, then for vertically polarized field, what is the variation in the azimuth direction? That is given by the first index. So, for HE mode the first index was 1, but as far as the linear polarized nature is concerned, it does not have any variation in the phi direction, because once the direction is taken care of, everywhere the intensity is going to be same for a given value of R. So, as I change the value of phi, the value of the electric field amplitude does not change. So, the HE11 mode then essentially becomes the LP01 mode. So, first index tells me that it is in the azimuth direction, there is no variation in the field amplitude. Second index 1 tells me that there are no zero crossing in the radial direction. So, the field distribution, this would be the linearly polarized LP01. Then the mode which are lying in a cluster like T0M, TM0M and HE2M mode, they will become degenerate and they will give the linearly polarized mode which is LP1M mode. So, here you will see one cycle variation in the azimuth direction and M will be the M minus 1 will be the number of zero crossings in the radial direction. So, if I consider the first set of these modes, so M equal to 1, that will give me a mode which is LP11 mode. So, if I consider in the BV diagram and if I take the next set of modes, this one, they will degenerate and they will give a field distribution which will be called as the LP11 mode. So, in the weakly guiding approximation, you have the first mode which travels, which is LP01, the next mode which will travel, which will be combination of these three, which will be LP11 and so on. Now, we have just talked about these two modes because these are two modes which are useful for long distance communication. LP01 mode, which is same as HE11 mode, of course, is the mode which propagates on a single mode optical fiber. But later on we will see that the next mode, which is LP11 mode, is useful in what is called dispersion compensation. So, later on when we discuss how to compensate dispersion on an optical fiber, that time we will refer back to this mode again, which is the LP11 mode. Now, just to see qualitatively how LP11 mode will be created. So, let us say I have HE21 mode, we have a TE01 mode, and since this combination here in this diagram, we have a combination of TE01, TM01 and HE21. TE01 and HE21 can give you a pattern, TM01 and HE21 can give you another pattern. So, we can see here, if I consider the HE21 mode and if I consider TE01 mode and if I add these two, you will see here the field direction is vertically upwards, here the field direction is vertically downwards, they cancel each other. When I come here at this location, the field direction is this way, here also field direction is this way. So, the field will add, and when I come to this location, this is going upwards, this is downwards, so field will cancel, and again here the field will add because this is the direction of the field here, this is the direction of the field here. So, the combination of these two fields essentially would generate a net electric field which will be a horizontal everywhere, but the intensity variation will follow a one cycle variation. So, this is the LP mode because the field is linearly polarized everywhere and in this case it is horizontal, and it has one cycle variation in the azimuth. So, its first index is 1. It also has cross 1 0 in this. So, its first solution, that is why it is the LP11 mode. So, a LP11 mode typically will have two intensity blobs like this, and the electric field will be polarized with the opposite direction. Instead of TE0, if I had taken TM01 mode and again HE21 mode, you change the orientation by 45 degrees, you get a combination of these two again, which will give me distribution something like this, because here when I come this location, the field get added, this location the field directions are again getting added, but in opposite direction. When we come here, the fields are in opposite direction, this is upwards, this is downwards, so it cancels, and same thing, there is a cancellation at this location also. So, again you see in the azimuth direction you have a one cycle variation, so it is LP1 mode, So, LP11 mode, there are two possibilities. One is I have these two intensity blobs and electric fields are going like that, or we have the two intensity blobs and the electric fields are like that. So, there are two possibilities for the LP11 mode, or in fact there are four possibilities for LP11 mode. For each of this thing I can orient this by 90 degrees. So, I can have four possibilities for LP11 mode. One is I can have the intensity blobs which are like that, and the field could be this way and this way, or it could be this way and this way. Other possibility is the 90 degree rotation of the coordinate axis, which would be like this. Like this. So, when we say we have a LP11 mode, in fact there are four modes which are having exactly same phase characteristics, and their intensity and polarization would be given by this. So, in fact, whenever we launch a light with arbitrary polarization inside a weakly guiding fiber, and if the excitation mode is LP11, in fact, we have a combination of these four modes which will be propagating simultaneously inside the optical fiber. Same thing then one can ask for what is the situation for LP01 mode, and LP01 mode as we saw is circularly symmetric. So, the rotation of the fiber does not play a role, but it certainly depends upon what is the orientation of the electric field. So, one possibility is this, other possibility is could be horizontally polarized, something like that. So, for LP11 mode we have a degeneracy by factor of 4, whereas for LP01 mode we have a degeneracy of factor of 2, because essentially we have two orthogonal polarization which are going to propagate in the form of LP01 distribution. Like that, if we consider the degeneracy for all the modes which are going to propagate for a large number, one can then sum up the total number of modes which are going to be present in each of these groups, and then one gets a result which gives us the total number of modes which are going to propagate inside the optical fiber, and that is approximately given by V square by 2. So, the total number of modes M is approximately equal to V square by 2. This is number of modes. So, if I consider a multimode optical fiber, and if the V number is much greater than 1, then approximately the number of modes which will propagate, considering all these degeneracies which we talked about, will be approximately given by V square by 2. So, if I consider a optical fiber with V number, let us say some 10, this will be 10 square, which will be 100 divided by 2. So, you will get about 50 modes propagating on the optical fiber. Of course, this relation is not valid when the V number becomes very small. So, if I take a V number of 2 or 2.5, then this relation will not be valid. So, this relation is valid when the V number is much greater than 1. So, in a multimode fiber, the V number is large, and because of this large number of modes propagate, and since each mode has its own effective index, you have a very large dispersion, and that is what we have seen from the multiple ray propagation inside the optical fiber. So, with this then one can come back and say that for the LP01 mode, which is same as the HE11 mode for a single mode optical fiber, you may have a field distribution which would look like this. So, you may have ALP01 mode which will be vertically polarized, or you may have ALP01 mode which could be horizontally polarized. And later on we will see the implications of this, just since we are having two orthogonal polarizations here. If the fiber was not perfectly circular, then the two modes will not propagate with the same phase constant, and it will have some effect on the performance of the data rate. But at the moment we should simply note that when we say LP01 mode, we essentially are referring to two modes which are having orthogonal polarization, which is horizontal or vertical, or any two orientation which are perpendicular to each other. So, if I now look at the BV diagram for the LP modes, as we have seen, the HE11 mode has become LP01 mode. So, this is more or less same as what we saw earlier. The cluster of three modes has now become LP11 mode, and then so on. So, now for a weakly guiding approximation, this is the diagram which is the diagram, because it gives you a relationship between the propagation constant beta and the frequency omega. And once we get these quantities here, essentially then we can find out the quantity which is d omega by d beta, which gives you the group velocity, and the phase velocity which is omega by beta. So, if we are operating in the frequency range or the fiber parameter range, where the fiber is a single mode optical fiber, then the location on this graph here gives you the quantity which is related to the phase velocity. I can measure the value of V, I can measure the value of beta, and except the proportionality constants, essentially the quantity which is V by beta will give me the quantity proportional to the phase velocity. Whereas this quantity here, group velocity, which is d omega by d beta, is related to the slope of this function. So, if I go to the curve somewhere here, essentially you will see that this quantity here, the slope of this will give me d beta by d omega, which is 1 upon this quantity here. So, here the slope is very small, here again the slope becomes very small, and that is the region where the slope is very large. So, you will see that if I calculate the group velocity, the slope here is very small, which is d beta by d omega. So, velocity is large here. Same is true when I go to this region also, and when I go here, that is where I get the velocity, which will be very similar to what I am going to get from the relation. So, the BV diagram, once we get for a particular mode, then by numerically calculating the quantity omega by beta or d omega by d beta, I can calculate the phase and the group velocity. And once I get the phase and the group velocity, then I can ask, if the energy was sent in the form of pulses, what will be the distortion of the pulses when it propagates on the optical fiber, and so on. So, having analyzed now the optical fiber in the form of this wave model, and having obtained this characteristic what is called the BV diagram, now the next thing would be to find out the group velocity, and then from there to find out what will be the distortion of the signal when it propagates on the optical fiber. So, the next topic which essentially we have to discuss is that if the signal is launched in the form of a pulse on the optical fiber, what way the signal will get distorted during propagation. Before we get into this question, however, first ask a question, what do we mean by signal distortion, and what are the conditions in general for signal not to be distorted. So, let us say suppose I had a system and suppose we put some signal x of t and this, we get from this system a signal which is y of t. We say the signal is not distorted while passing through this system if yt is a replica of this signal xt. However, while saying replica, if the amplitude of this signal as a whole is reduced or increased, then we do not call that as a distortion. For example, when we are speaking, let us say our voice is passed through an amplifier and given to a loudspeaker, the signal amplitude is increased significantly, but that we do not call a distortion, it is simply increase in amplitude. Similarly, when we speak from this location, by the time the sound reaches to somebody else, it has taken some finite time. So, a sound reached there after some time. In other words, the sound was delayed in time at the receiving point, and then also we do not call as a distortion. So, when the signal is reduced or increased in amplitude as a whole, we do not call that as distortion. If the signal is delayed in time, then we do not call it as a distortion. What that means is that if the signal y of t is a times some x t minus tau, if we get that, then we say my system is a distortionless system. If this thing does not happen, then we say the system produces distortion. So, any signal undergoing through amplitude change as a whole and delayed in time is not called a distorted signal. One can then ask a question, to get this behavior in time, what should be the frequency response of this signal? So, if I take the Fourier transform of this signal, you can get y of omega, that will be equal to a x of omega e to the power j tau omega. What this gives us now then is that the frequency response, which is y omega divided by x of omega, that is equal to a e to the power j tau omega. So, to have a system distortionless, two things have to happen. First is the amplitude response, which is given by this, should be independent of frequency, and the phase response, which is given by this, is linear with frequency. So, we should have amplitude response constant as a function of frequency and the phase response linear with frequency. If these two conditions are satisfied, then there will not be any distortion of the signal when the signal passes through the system. With this understanding, then let us now go to the optical fiber and ask a question whether these two conditions are satisfied. And if they are not satisfied, then only we will get distortion on the optical fiber. If these conditions are satisfied, then we will have a distortionless propagation on the optical fiber. Before we get into that, however, let us first look at the fundamental difference between the optical communication and the normal radio communication. When we talk about a radio communication, we have a carrier and we have a modulating signal. Same thing we do in optical also. We have a carrier which is the optical carrier. We modulate this by the signal which we want to transmit. However, when we go to radio frequency, if you ask what is the spectral width of the carrier, and invariably this question is not even asked, because the spectral width of carrier which you get at radio frequency is so small that we do not have to take that into consideration. So, if the radio frequency, if I consider a signal, if I have a frequency, carrier frequency, which is given by, let us say, some f naught or fc, and if I have a modulating signal, frequency, let us say fm, and let us say if I do the simple amplitude modulation of this, we get frequencies which are fc plus fm, fc minus fm, and the carrier frequency fc. So, if I look at the spectrum of a signal which is AM signal, we get a carrier frequency which is fc, we get what are called the side bands which is fc minus fm, and we get fc plus fm. So, at radio frequency, since the spectral width intrinsically is very small for carrier, you see the frequency spectrum which consists of 3 delta functions, one located at fc and the side bands located at fc plus fm and fc minus fm. So, at radio frequency, if I take an amplitude modulated signal and put on spectrum analyzer, you will really see the 3 sharp frequency peaks in the spectrum. Question one can ask is, when we go to the optical frequencies, is the same picture valid at optical frequencies also? So, let us say we have the so called carrier frequency at optical signals, and then that carrier signal is modulated by frequency which is again fm. But in optical signal you have a spectral width which could be of the order of about a few nanometers. We have seen earlier that if I consider a source like laser, you can have a spectral width typically of the order of about 1 to 2 nanometers. If you have a source like LED, then we can have a spectral width typically of the order of about 20 to 30 nanometer. And we have seen if we go to typically 1 micron wavelength kind of signals, approximately 1 nanometer spectral width is 100 gigahertz. So, we have almost a rule of thumb that typically 1 nanometer is of the order of 100 gigahertz. So, if I have an optical carrier whose spectral width is 1 nanometer, then this carrier, if I look at the spectrum analyzer, it will not look like a delta function, it will look like a distributed spectrum with a frequency range effectively of the order of about 100 gigahertz. So, if I look at the carrier without modulation, the carrier will look something like this. This is my center frequency f0, and typically this will be of the order of about few 100 gigahertz. So, now there is a fundamental difference between the way the optical carriers are modulated and the radio carriers are modulated. In the radio, the spectral width of carrier is negligibly small compared to this frequency, which is FM. Whereas when we go to optical signals, the spectral width of carrier is not only comparable, but will be much larger compared to the modulating signal. And obviously, when this thing happens, something fundamentally changes, conceptually changes. So, the modulation process in optical is not same as what we can visualize for the radio signals. So, radio signals we have very clearly seen the carrier and we can very clearly see the sidebands. So, when we go to the optical signals where the spectral width of carrier is very, very large compared to modulating signal, we have to now visualize this modulation process little more in depth before we make any conclusions. And precisely this is what we will do when we meet next time. We ask a question: if we take a light source which is having a spectral width few hundred gigahertz, and if I try to modulate this with a modulating signal which has a frequency maybe few gigahertz, what way the spectrum will be represented? What will be the implication of this for the signal transmission? And what will be its implication for the distortion of the signals on optical fiber? So, although in first look from the ray model as we saw earlier, when we have a simple one ray propagating along the axis of the fiber, there was no dispersion. So, first look it might appear that if I use a single mode optical fiber, there will not be any distortion of the signal in the optical fiber. Essentially, we have to understand this phenomena in depth before we make that conclusion. So, next time when we meet, essentially first we investigate in this situation when the spectral width of the carrier is very large, how the modulation can be visualized, and then we answer the question, what would be the distortion of the signal on the optical fiber.